Good day, embedded RISC-V aficionados. This time I'm diving deeper into the CH582 RISC-V MCU to show you how to handle EEPROM, serial, timer and SPI to drive a NeoPixel strip. For starters, I want to set the stage again. My development environment is based on the Moonriver Studios IDE running on a Linux Mint PC. As I detailed in my previous hack on this subject, I created some bash scripts to make things easier. In this project, I have updated Moonriver to version 1.80. I also came across some anomalies in the example programs given on the WCH GitHub. For an unknown reason, the individual examples given tend to exclude some references to the libraries for other peripherals. This can easily be solved by editing the .c project file. More on this later. My aim here is to dive into several peripherals covering more advanced concepts, such as interrupts and port reassignments, as well as fixing some of the oversights in the GitHub examples. The idea is to go beyond Blinky. That said, we will actually be blinking the LED, using the timer interrupt, as well as running a NeoPixel strip from SPI. How do we get this project up and going in Moonriver? Create a separate directory to use as a Moonriver workspace. Open Moonriver using the directory just created as workspace. Select the Create a New Moonriver Project option, selecting the CH592F board. Replace the usr/main.c file with my example given in the Files section of the blog. You will then need to edit the .c project file to liberate all of the peripheral drivers. Although I developed this project on a CH582 board, I specified the 592 because there is no repo for the 582 board, only the 583, and the CH583 repo does not include samples for SPI0. The 83 has two SPI interfaces, but the 82 only has one. At this point, it is a good idea to close the IDE and edit the .c project file outside of the IDE. It should be located in your workspace/CH592F directory. We will need to change the word excluding in line 263 to including. This will liberate the excluded drivers in the std-perif driver directory so we can use them later. Now we can restart the IDE and get to work.
Pin assignments.
Most development boards for the CH500 family use the smaller F series microcontrollers, which have a limited set of I/O pins on the chip. This can be exacerbated by board designs that may or may not bring out all of the available pins. For this reason, I wanted to include examples of how to select alternate pins. I found that I needed to do this after reviewing the I/O that I wanted to use for this project, and carefully reviewing the documentation for the microcontroller I'm using. My constraints were not to use PA8, where the onboard LED is connected on many boards, as well as to be able to use SPI0 for the megapixels. We also need to be aware of the USB pins so as not to interfere with uploading during the development process. I also want to try to use a WCH Link-E programmer on my own board designs.
Serial example.
We start with a serial example derived from the example auto-generated when we created the Moonriver project. The IDE is nice enough to provide us with stdio functionality for the serial ports, although we see some examples using a print function and others using a non-formatting function. Printf is available once the serial port is configured using the included driver. I've been writing in C for too long and I can't live without printf. Most of the CH500 chips offer up to 4 serial ports with an alternate pin arrangement available for each. That said, the CH582F module I used to develop this project only left me with one choice for the serial demo. I ended up with UART0 on the default pins. I wanted to include an example of selecting alternate pins in my code, so there is an unused function in the uartpins.c file where I illustrate selecting alternate pins for UART3. The default UART used by the printf function is specified in the compiler instructions given in the .c project file. You will see my change on line 128.
Value equals debug equals 0.
This only affects the UART selection itself. Selecting alternate pins is done in our configuration code. So in the end, we will only get to learn about using interrupts as they relate to more advanced functions for the UART serial peripheral. I use them to receive characters to drive a simple user menu. Unlike printf, scanf is not available.
Serial setup.
We only need to set up the TXD and RXD pins as follows. My UART0 pins std function contains. After this, we can use printf for the application and/or debugging.
EEPROM.
The CH500 MCUs do not have true EEPROM capability, but the libraries provide utilities to use data flash for the same purpose. You will see these used in various parts of my example code. My little user menu system allows the setting of various application parameters, as well as a method to save them and a method to clear the EEPROM.
Timer 0 with interrupt to blink the LED.
The CH500 chips contain 4 26-bit timers with GPIO output facilities. It would have been convenient to use a timer GPIO to flash the LED, but the LED is on pin A8 on the board I am using, which has no connection to any of the timers. A8 is the UART1 RXD pin, which is one of the reasons I chose to use UART0. To make things interesting, we are going to offer a menu option to change the duty cycle of the LED blinker. We do this in the interrupt service routine by reinitializing the timer on each interrupt. We could have used the PWM mode of the timer or even one of the separate PWM peripherals, although the latter is not real good at low-frequency operations due to being only 8-bit. Drop me a line in the comments if you would like to see a deeper dive into timers and PWM in another project. We only need 3 lines of code to set up the timer. The first line just sets the high watermark of the timer's counter. This will cause an interrupt to be generated. The other 2 lines configure just that condition to be the interrupt source, and then enables interrupts for timer 0. The interrupt service routine is somewhat complex, because we are changing the time count every IRQ to achieve the effect of a variable duty cycle. I recommend examining the source code given in the files section of the accompanying blog for a closer look.
SPI setup for NeoPixels.
We are going to use SPI0 to generate the pulse stream needed to do some lighting effects on the NeoPixel strip. I recommend you check out one of my other blogs about using SPI for NeoPixels. The SPI setup is quite simple. We only need to do the default SPI master initialization and set the clock frequency. In this case, I determined the frequency empirically using the logic analyzer. We are using the MOSI pin to output the pulse stream to the NeoPixel strip, so need to set MOSI to output. In this example, I am also setting the CS pin to output, but only for the benefit of the logic analyzer. I have written up a couple of routines to light up some pixels in a meaningful way. The show routine just displays a buffer of pixel colors. The BOP routine takes each of the colors from the previous array and sends them running them down the strip for an attractive effect. I hope you found our deeper dive into the CH500 family of RISC-V MCUs to be interesting and informative. Check the description for links to the blog for this project. Keep in touch via the comments letting me know where else we should go diving. There are more peripherals to discover. Thanks for watching. Please like and subscribe. You know the routine.